This presentation is about risk analytics and artificial intelligence. As a working example and to make my case, I will talk about wrong-way risk for clearing houses. The strategy regulators recommend to manage wrong-way risk is based on collateral add-ons to base margin. They also recommend to carry out extensive simulations based on hypothetical scenarios and carry out a reverse stress testing analysis. To quantify the effectiveness of these remedies, I will also calculate metrics for the default fund contribution based on the same hypothetical scenarios. Another point I will touch upon is the use of blockchains for models and risk analytics and the client-side calculation of risk analytics. This technique is useful not only for the accurate estimation of wrong-way risk but also for other applications, such as cross-margining strategies between exchanges. The other topic I wish to cover is artificial intelligence. The abilities demonstrated by GPT-4 are quite incredible and to a large extent surprising and unexpected. For sure, AI is here to stay, and it is now important to figure out what impact it is going to have on financial infrastructure. Apparently, the single biggest limitation of AI is planning. Meaning, AIs lack the ability to take decisions and plan out strategies, especially if under conditions of uncertainty. I am confident AIs will fill this gap, but the question is how. Finance happens to be based on decision theory under conditions of uncertainty. That's what finance is from a mathematical point of view. If we can get LLMs to generate codes in a modeling language to express finance problems, and we have a solver for that also, LLMs will become the human interface to risk solutions. The task of creating natural language interfaces to risk analytics will give a big impetus to the development of compiler technologies and modeling languages that AIs can be taught how to program. That's interesting also in relation to blockchains and distributed ledger, because also these technologies crucially depend on compilers. So far, DLTs have been confined to trade capture and settlement. Going forward, compilers for risk and pricing suitable to LLMs will make it possible to blockchain also market data and financial risk models, the very bricks that make up financial infrastructure. Finally, I would like to address the broader question of what can we call artificial general intelligence in the finance domain. I personally would be happy to talk about AGI if we succeeded to break down decision silos and have enterprise-level risk management, but I'd like to hear your opinion about that. This is all I wish to discuss here, and will use the case of wrong-way risk to explain myself. I can also imagine cases where mathematical finance finds non-financial use cases and have a major impact on AI more broadly, teaching AIs the art of strategic planning. But that's not something I can cover today. In the past, mathematicians invented deep and rich theories but could not design anything close to artificial intelligence. It's not that they were not clever. The point is rather that nobody even knows how AIs work today. Large language models have not been designed from first principles in a traditional sense. We have simply connected them to the internet and let them evolve powered by large GPU clusters. The essential bit that past generations were missing was the GPU clusters. But why is that? What are GPUs used for? The answer is quite simple. GPUs are used to multiply matrices. Mankind has known about matrices for a very long time, but we just lack the technology to multiply them. Squaring a 100 by 100 matrix takes as many as 2 million floating point operations. There's no way one can do that by hand. So people invented clever workarounds, and most of mathematics research originated from the desire to understand them. In the specific case of finance, the toolkit included special functions, as for instance in the Black-Scholes model, PD methods, as in lattice models, Fourier transforms, as in the Heston model. When computers arrived, things still did not change for a long time. Up until the year 2000, it was still practically impossible to multiply two matrices with one another efficiently. So people still used a vast repertoire of tricks and shortcuts which they turned into code. To figure out which algorithms would perform better than others, people would simply count the number of operations required for its execution, also called Turing complexity. Up to the year 2000, the mathematicians and computer engineers worked independently of one another. Mathematicians tried to reduce Turing complexity. computer engineers tried to increase clock frequencies of CPUs. Then around the turn of the century, everything changed. At the turn of the century we had a multi-core crisis, and clock rates stopped increasing. It was simply not possible to run CPUs too fast as they would produce too much heat and melt the silicon. As you can see from this plot, clock rates flattened out and efforts in computer engineering had to be redirected toward multi-core architectures. Multiple single-core CPUs could fit on the same die. Still, a staggering 90% of the transistors were in caches to ferry data in and out instead of doing useful arithmetics. Some starting to think that CPU designs had reached their limit, and the time had come to go back to the drawing board. A big leap happened with the introduction of GPU architectures by NVIDIA and ATI. They followed up to ideas developed at Silicon Graphics, taking them far ahead. GPU designers did not attempt to optimize old-fashioned algorithms and focused instead on the graphics market. They inserted thousands of cores and did not invest much in memory caches. This decision turned algorithmic optimization upon its head. Turing complexity was no longer proportional to execution time, and only one class of algorithms stood a chance to be efficient: matrix multiplication. The reason why GPUs are great at multiplying matrices is easy to understand. Consider, for instance, the problem of multiplying two square matrices of size n. The memory to store a square matrix grows like the square of the size, while the number of floating point operations needed to multiply two square matrices grows like the cube of the size. No matter how tight the memory bottleneck is, if an algorithm has its bottleneck in matrix multiplication, all the thousands of cores will be kept busy and performance will be stellar. The newly found ability to multiply large matrices was a total game changer. Traditional algorithms were not only inefficient, but also no longer needed. People soon realized the implications and began to develop applications based on matrix algebras. As I mentioned, matrix algebras are pervasive in all areas of applied mathematics, including finance. In finance in particular, we use probabilistic models to capture uncertainty. A probabilistic model for the evolution of any observable, such as a stock price or a rate, can be described by specifying the values the observable can attain, and the probability matrix for it to hop from one value to another within an elementary time step. To find the probability that the observable will attain a certain value over a longer time interval as a function of the starting point, one has to multiply transition probability matrices with one another. Neural network models are at the basis of language models and pattern recognition models. By design, they also have a numerical bottleneck in matrix multiplication. Neural networks work with a state vector X and build a model for its evolution over time by combining three operations: a multiplication, a matrix of weights, a shift by a vector representing a bias, and a nonlinear transformation by a so-called activation function. And let's not forget Mother Nature. Nature is a majestic calculator that apparently solves the Schrödinger equation at all times. The Schrödinger equation is also a matrix equation and looks very similar to the equations of probability theory. The difference is that the state vector is complex valued and an imaginary unit multiplies the time coordinate, but that's a technicality to some extent. The mathematics of quantum mechanics can also largely be used in finance. To take advantage of GPUs, at Global Valuation, we reformulated mathematical finance in terms of matrix algebras. To do that, we borrowed key concepts from quantum mechanics, such as time-ordered exponentials. In the brave new world ruled by matrix algebras, there are three types of errors young generations should avoid. A type 1 error happens when one insists on using an outdated model. Old models are highly constrained and owe their existence to some mathematical shortcut that makes them solvable. If we can master matrix multiplication, there is no reason to suffer of these limitations. A type 2 error happens when one uses a neural network model to solve a valuation or risk problem which must instead go by the rigid rules of mathematical finance, not to give rise to arbitrage opportunities. Type 3 errors are a combination of Type 1 and Type 2 errors, and judging by the articles on Risk magazine these days, they are the most common. These are error 1 commits if one insists on using inefficient algorithms based on outdated mathematics and combines them with interpolation techniques based on neural networks and borrowed from machine learning. This combines the shortcomings of highly constrained models with uncontrollable violations of the arbitrage-free conditions due to the use of neural networks. Generations of philosophers dedicated their work to this triangle, and still, it is quite surprising to see it appear nowadays everywhere in reference to AI intellectual abilities. On one vertex there's the physical world. We distill selected features from the physical world and express them by using natural languages. Based on these simplified and stylized views, we then build models which we can solve mathematically and project out future scenarios which are possibly contingent to our actions. We then optimize with respect to some utility function and select a course of action in the real world. If we witness unintended consequences and decide they are not acceptable, we go back to the drawing board, improve the model, and repeat the cycle. Here below is a quote by Stuart Russell, a computer science professor from UC Berkeley that recently signed off on a document asking for a moratorium period for AI deployments.
We have, I think, basically chanced upon this idea that by expanding from unigrams to bigrams to trigrams to 32,000 grams, something that looks like intelligence comes out. The bulk of work in AI since the 50s has been on actually understanding how intelligence works. So how does reasoning work? That's actually a question that philosophers and logicians have worked on for thousands of years and come up with a very good, thorough, complete analysis. And we have both mathematical and software tools that can do logical reasoning with remarkable complexity. Now, so we might argue that actually the underlying intelligence should be more of that form, and the language model should be the interface to it. And that would be probably a much more reliable system because we would be able to provide it with knowledge whose content we understood and be sure that it knows it because it's in the knowledge base and the system is reasoning correctly underneath the language layer.
Following Professor Russell, in the specific case of finance, we should use LLMs as an interface in plain English that will allow us to program and customize risk analytics systems. However, the latter will have to be constructed rigorously according to the established principles of mathematical finance. Bill Gates seems to be in agreement. Let's hear what he said in a recent interview.
It also, in terms of how hard it should work on a problem, when you and I see a math problem, we know, wow, I may have to apply simplification 5 or 6 times to get this into the right form. And so, we're kind of looping through how we do these reductions, whereas today, the reasoning is a sort of linear chain of descent through the levels. And if simplification needs run 10 times, it probably won't. So, math is a very abstract type of reasoning. And right now, I'd say that's the greatest weakness. Weirdly, it can solve lots of math problems. And there are some math problems where if you ask it to explain it in an abstract form, make essentially an equation or a program that matches the math problem, it does that perfectly, and you could pass that off to a normal solver. Whereas if you tell it to do the numeric work itself, it often makes mistakes. And it's very funny because sometimes it's very confident that, hey, or it'll say, oh, I mistyped. Well, in fact, there's not a typewriter anywhere in this scene. So the notion of mistyping is really very weird.
My interpretation of what Bill Gates is saying here is that it is already an entirely unexpected miracle that LLMs can play medical doctor or lawyer or correctly generate simple codes. There is no point to teach LLMs mathematical reasoning. All one needs is to teach LLMs to state mathematical problems and provide a generic solver, presumably a matrix engine, to work out a solution. What is not trivial and takes a lot of research work and innovation is to build what Bill Gates refers to as a normal solver, which is capable to solve all problems in the vast domain of risk and pricing, or equivalently, of decision theory under conditions of uncertainty. In the finance domain, we need three ingredients: a modeling language that allows to formulate all mathematical problems in risk and pricing, a compiler that will fill in all the details regarding maths and concurrency, and a solver, as a matrix engine, that will execute efficiently. This pretty much defines the product that we have been building in our group starting in 2006. But let me recount the story of how we got there. In the first stretch of his academic career, Claudio worked in mathematical physics and in particular on quantum mechanics. He transitioned to finance in the mid-90s where he started a master's program in Toronto. He was teaching mathematical finance a bit abusively because his position was in mathematical physics. Claudio discovered soon enough that there are some radical scientific differences between physics and finance. Physics is about the laws governing the physical world, while finance is about strategy optimization. Concepts such as arbitrage freedom in finance do not have an analog in physics. Other differences are more superficial. For instance, the mathematical formalism of probability theory is very different, as physicists use matrix algebras while most finance people have traditionally used stochastic calculus. But that does not mean matrix algebras cannot work equally well in finance. On the contrary, they do. Prior to 2006, Claudio's work in finance was about analytically solvable pricing models. He had built the most far-reaching extensions of the Black-Scholes formula, adding to implied volatility as many as 10 additional parameters in 4 different ways. The research was well received and it earned him a chair in mathematical finance at Imperial College in London. However, Claudio was frustrated as it was difficult to apply the results. You can have 10 parameters in a model, but if the parameters do not have a direct economic meaning, they are not very useful. He came out of this experience wanting to solve economically motivated models where we are free to specify anything. In the year 2006, the ongoing multicore crisis motivated Claudio to build finance models with the bottleneck concentrated in matrix multiplication. He also chose to work within the vast class of hidden Markov model and its full generality, and to avoid model-specific shortcuts. Interestingly enough, Claudio was not alone in his interest in HMEMs and matrix algebras. Also, Jeff Hinton and his increasingly vast following in the machine learning community made the same choice and for the same reasons. One of the differences between machine learning and finance is that ML is backward-looking and estimated on historical time series while finance is forward-looking and models are calibrated to option prices. Another major difference is that in finance asset price processes are constrained to be martingales. Machine learning instead is entirely unconstrained. Apart from these two differences, the alignment between finance and the matrix formalism and artificial intelligence is deep-rooted. Finance and more generally decision theory under uncertainty, once everything will be said and done, may well end up being integrated as a chapter of AI in the final construct. At Global Valuation, we engaged in this research direction of rebuilding finance with matrix algebras. We did not expect this would take us 17 years and counting and that there was so much to uncover. But let me summarize to you what we learned along the way. We first discovered a peculiar and unexpected error cancellation mechanism that ensures calculations carried out in single precision are far more accurate than one would expect based on a naive back-of-the-envelope estimate. Once we understood the magic of this cancellation mathematically, we wrote the paper quoted on this slide. Also in machine learning, something similar is at work. In fact, ML algorithms are often run in single, or even half precision. This is very important from a technology standpoint because the multiplication of lower precision matrices is much faster than the multiplication in double precision, by a factor 8 for single up to a factor 100x for half precision. We also convinced ourselves that all models described by a generic hidden Markov model could be solved by the exact same algorithm, no matter how the model was specified and what was the asset class. A universal solver for all problems in risk and pricing seemed a very valuable tool because one could build pricing models that accounted well of econometric properties of risk factor time series. However, being able to build better models turned out not to be the only benefit of a universal solver. There were several other benefits. An additional benefit of having a universal solver was scalability. When in 2009 we were challenged by a client to build a large-scale CVA calculator, we came to realize that by treating all risk factors on the same footing, the portfolio engine turned out to be eminently scalable. The plethora of clever shortcuts used in derivative pricing stand in the way of optimization on modern hardware because they are model-specific. Instead, we were able to easily vectorize our codes across payoffs and across models. Vectorization is key to enable unparalleled levels of scalability and performance. Having built highly scalable pricing engines, we started contributing to classical finance in areas such as funding risk, cost of capital, model risk, reverse stress testing. The key point of originality of this research work was the emphasis on enterprise-level modeling. This applies also to the case study I present here, and I will give you shortly an example of our approach to reverse stress testing and wrong-way risk. More recently, we created a modeling language and have built a compiler called Esther. Esther is a compiler like no other because it fills in mathematical and orchestration details for the vast finance domain. The Esther compiler lies on top of mainstream compilers. The Esther modeling language is actually defined by extending mainstream programming languages such as C#, TypeScript, and Python. What Esther does is to produce GPU codes by reinterpreting the constructs. We then have a separate solver which works out the numbers. The reason why we developed the Esther compiler was to factor out the difficult bits and make it easier to program our software. We expected interesting interactions with machine learning since we all use HMMs, and it would have been interesting to both estimate HMMs historically and, in addition to that, calibrate also to option prices. What I did not expect was that large language models would potentially provide a natural language interface. This came as a surprise. In the next part, I will discuss the case study on wrong-way risk that I have mentioned. Wrong-way risk, also known as WWR, arises from the correlation between counterparty default risk and market risk factors. A situation of WWR occurs when a clearinghouse member is exposed to a market risk factor to such a degree that a sudden change in value could jeopardize the solvency of that member. Correlation drivers for WWR are typically shared across several members. The impact of WWR on the solvency of a clearinghouse is difficult to assess with member-specific metrics, but is best done from a top-of-the-house view. WWR calculations are similar to CVA calculations used by banks to value and hedge the cost of counterparty credit risk. However, there are some differences between the two. In the case of clearinghouses, WWR calculations are simpler than CVA for one reason, but more complex for several others. The main reason why WWR for clearinghouses is simpler than CVA is that it only requires a short-term time horizon. On the other hand, a reason why WWR is more challenging than CVA is that in WWR, modeling an event of member default must be done as a binary default/no default event. In contrast, in CVA calculations for banks, an approximation is often used to model the probability of default, PD, of a counterparty. This approach only works when dealing with thousands or tens of thousands of small counterparties. However, when there are only a few large members, such as in the case of 100 large banks, it does not make sense to assign a probability of default to each individual bank. For instance, stating that JP Morgan defaults with a probability of 15% in a particular scenario is not informative, as it would make a significant difference whether or not JP Morgan defaults. A weighted average of the two cases is not meaningful. Secondly, since we also need to calculate the impact of WWR strategies on default fund contributions, it is necessary to generate a large number of scenarios. A rough calculation shows that we require approximately 10 million scenarios for a clearinghouse with around 100 members to obtain sufficient statistics for default fund contributions. In contrast, banks execute CVA calculations with around 100,000 scenarios, and some banks even generate fewer scenarios. Another complication arises when attempting to fully assess the correlation between counterparty default risk and a market scenario. Ideally, one would want to run scenarios on the full portfolio held by the counterparty. I will revisit this issue later when discussing permissioned analytics. For the case study presented today, it is assumed that members do not hold any other positions in risky assets in addition to those in the cleared portfolio. Regulators have made reference to WWR in several publications over the past 12 years and have advocated two types of risk management strategies for addressing WWR. The first strategy is to use collateral add-ons in addition to base margin computed with a VAR model. The second strategy involves carrying out reverse stress testing analysis, generating many hypothetical scenarios, and identifying critical ones that could potentially lead to significant losses for the clearinghouse. Collateral add-ons can also have an impact on default fund contributions. If properly defined, WWR add-ons should reduce default fund contributions along with enterprise-level risk. In general, collateral add-ons result in a redistribution of collateral requirements. When implementing a WWR model, it may be possible to revise the model for base margin by adjusting, for instance, the quantile used for calculating VAR. By doing so, the introduction of collateral add-ons for WWR can lead to an increase in total collateral requirements for some members and a decrease for others. In other words, WWR add-ons can result in a reallocation of collateral. The effectiveness of this reallocation can serve as a good measure of the quality of a WWR policy. Even if the total amount of collateral required by all members remains the same, a margin policy with WWR add-ons should reduce default risk for the clearinghouse. Reverse stress testing is a useful tool for analyzing risk exposures and identifying the primary drivers of potential critical losses. I have worked on reverse stress testing schemes for many years, starting with XVA portfolios. The approach involves generating a large number of scenarios, calculating the total cost of capital, and then determining how the cost of capital would change if one scenario were to be omitted. Scenarios that result in the most significant reduction in cost of capital are deemed to be the riskiest. In the case of clearinghouses, the cost of capital is relatively easy to evaluate with a single-period simulation, as multi-period simulations are not required as they are for banks. Essentially, the cost of capital is the default fund contribution itself. Once again, all of the metrics we calculate are essentially enterprise-level metrics, and not specific to individual members. The specific criterion used to identify the WWR collateral add-on is taken from regulatory documents and can be formulated as follows. The WWR add-on for a member is calculated as the collateral amount that, when added to the baseline initial margin, reduces the credit valuation adjustment, CVA, of the member to the level that would be calculated under the assumption of no correlation between market risk and the credit of the member itself. For our numerical experiment, we consider a clearinghouse portfolio comprising 100 member positions and a total of approximately 500,000 cleared trades in equity indices, single stocks, European and American stock options, forwards, warrants, and dividend swaps. We use synthetic portfolios for members generated according to various different criteria, including random portfolios, where positions are randomly generated; hedged portfolios, where all out-of-the-money puts are long; long-only portfolios, containing long index positions, long calls, and short puts; short-only portfolios, containing short index positions, short calls, and long puts; insurance portfolios, containing only short out-of-the-money put positions. We also ensure that the portfolio is clear, i.e., each long position is matched by a short. We use a defaultable SLVJ model for both the cleared equities and the member credit processes. SLVJ stands for Stochastic Local Volatility Model with Jumps. These are the most sophisticated and comprehensive pricing models for the combined credit equity process because they combine all the features: local vol, stochastic vol, jumps, and default events. The reason why we use SLVJs is that they are cutting edge and a recommended best practice. The reason why we use defaultable equity models is that we want to model WWR consistently across the underlying risk factors for cleared trades and the default process for members. The regression copula model we use is fairly simplistic and uses the equity index as the sole factor. However, there would be no additional complications with using multiple betas. If we were to use permission analytics, we could discover the betas by running analytics client-side. Historically, equity option models based on the ease of pricing European options with a mathematical shortcut or another. The simplest model was by Bachelier, then followed Black-Scholes and many others, each integrating a feature lacking in the precursor models at the cost of a more costly numerical solution. Using solvers based on matrix algebras, all model specifications are on the same footing and execution times only depend on the sizer of the Markov generator. Also, all payoffs can be used for calibration purposes, not just European options. In particular, in the case of equity clearing, most single stock options are American style, not European. Also, it is important to imply future dividend payments by combining option and forward prices. Something similar happened in classical statistics, where the most popular models such as GRCH were selected and studied based on the ease of calculating the likelihood function required for estimation. Machine learning eliminated all that. Matrix algebras not only enable a quantum leap in the quality of market data calibration, they also enable blockchaining of models. The combination of these two features can potentially redefine the market data distribution market. Pre-calibrated and immediately usable models will greatly facilitate the work of risk analysts. This graph shows a sample comparison between two collateral strategies. In the strategy on the left-hand side of the page, we use expected shortfall with a modest quantile level of 97.5% to calculate the base margin and add WWR collateral add-ons to it. In the strategy on the right-hand side of the page, we instead use expected shortfall with an extreme quantile of 99.7% to calculate the base margin but do not include WWR add-ons. The result is a collateral reallocation, as the total amount required, including base margin, add-ons, and default fund contributions, is similar, at $570 million versus $542 million. However, the risk to the clearinghouse in the presence of WWR add-ons is significantly reduced, and default fund contributions are also reduced. To better understand the differences between the two strategies, we can begin by examining these pie charts of the base margin. Here, we observe that the distribution of members across portfolio strategies is nearly identical in both cases. This pie chart pertains only to the strategy with add-ons and illustrates that the majority of the additional collateral is contributed by members holding insurance portfolios, i.e., portfolios that exclusively comprise short put positions. In the absence of WWR add-ons, the losses that a CCP would bear are primarily attributable to members with insurance and long portfolios. However, in the presence of WWR add-ons, these members are far less concerning, as the left-hand pie chart illustrates. The distribution of default fund contributions is also highly sensitive to the inclusion of add-ons. Without WWR add-ons, members with insurance portfolios are required to contribute the largest share. However, with the inclusion of WWR add-ons, the distribution is more balanced, and the amounts required are significantly smaller. Ultimately, the cost of funding to a member to pledge both collateral and capital is greatly reduced in the presence of WWR add-ons. Default fund contributions, in fact, incur a Tier 1 deduction and a full hurdle rate of perhaps 14%. In contrast, margin collateral is far less expensive and can be obtained from clients. Finally, these pie charts illustrate the results of a reverse stress testing analysis. The riskiest scenarios differ significantly depending on the collateral strategy. The key takeaway is that loss events for the clearinghouse are attributable to very different sets of cleared equity names when comparing the two cases with and without add-ons. There are other considerations which matter for clearinghouse margin models, such as for instance the pro-cyclicality impact of margin policy and backtesting. However, the definition of a treatment for wrong-way risk add-ons should take priority on both pro-cyclicality and backtesting as it fundamentally alters risk profiles. Here you can see the user interface of the Ester compiler. As you see, it runs in a browser. Here I am using Edge because I like to organize my all projects using vertical tabs on the left-hand side, but it would run in any other browser. The Ester compiler and solver are configured in two separate Dockers. A user can access the compiler with a browser without any local installation. Otherwise, the user may install either the compiler alone or both items locally. The solver Docker does not require storage capabilities and is diskless. It communicates with the client via gRPC. The IDE is OpenVS Code, a browser-based version of Microsoft Visual Studio Code. Here you see a project implemented in C#, but also other mainstream languages can be supported. With C#, IntelliSense is supported by the OmniSharp extension, and we make available a fully functional Samsung debugger. There is also a terminal with Ubuntu as operating system. It all works in a browser precisely as it would on a local installation. I store all my source codes locally. We need GPUs for the server, of course. We support the GPUs by NVIDIA and AMD, and we also support Apple M1 and M2 processors. To create a portfolio in Ester, one has to define a dependency tree to host all the trades and their constituents, and to also host the portfolio itself. Each node in the tree inherits a class of type observable. Here you see the class that defines the portfolio over which we want to implement reverse stress testing. Let me now show you the class where I define American options. As you can see here, we have functions eval and callMount which specify the payoff and the American style optionality. We can also define pricing models in full detail. Let me show you the class where I define SLVJ models. Let me now start a run and show you the log. The log entries in white with black background are produced by the client, while instead the log entries in black on a white background are produced by the server. At a first stage, Ester generates all the Markov generators client-side and ships them asynchronously to the server. Then the compiler generates intermediate codes for payoffs and risk analytics and ships them also to the server. In turn, the server generates hardware-specific codes, runs them, and sends scenarios back to the client by invoking a sequence of callbacks. In a first stage, it generates all transition probability kernels. Then it generates all CUDA codes and starts the Monte Carlo simulation. It generates scenarios by batch and ships them to the client by means of a callback. It is then up to the client to execute user codes to find the desired risk analytics and create reports. As I mentioned earlier, I decided to develop the Esther compiler because I already had a flexible universal solver for all pricing models in the HMM class. My goal was to lower the barrier to entry for building risk models with matrix algebra by factoring out the mathematics. Going forward, I expect that large language models will be capable of programming Esther in full generality, and developers should focus on training LLMs on a broad range of use cases. Another application of the Esther compiler is related to blockchains. There has been a growing trend towards blockchain-based trade data by representing payoffs in an executable format. The Esther compiler enables the extension of blockchains to pricing models and aggregation logic for risk analytics. I anticipate that this will lead to groundbreaking innovations, such as the secure calculation of risk analytics on the client side. For example, a member of a clearinghouse could agree to calculate margin analytics on hardware under their control whenever the clearinghouse initiates the calculation. Potential applications of this technology include more accurate WWR assessments that incorporate a member's full portfolio and cross-margining between different exchanges. Another class of applications involves pre-calibrated, blockchain-based market data. The vision we have for financial services is roughly summarized in this graph. The standardization of calibrated pricing models enabled by the Esther compiler can help clients bypass the need to recalibrate models from raw data or, at the very least, speed up the calibration process by providing high-quality starting points for optimizers. Blockchain-based analytics definitions would allow for the execution of certain analytics on the client side. For example, if a clearing member could run the margin calculator against all clearinghouses, they could potentially use a position versus one clearinghouse as a hedge against another. Blockchain-based trade descriptions, models, and aggregation logic contain data and descriptive codes that roughly correspond to natural languages. These three elements could conceivably be generated automatically by large language models and validated through testing before being used. Before concluding, I would like to address the question of how we might define artificial general intelligence, AGI, for financial services. I looked up the Wikipedia page and found two definitions for AGI. Criterion 1. An AI is called AGI if it can accomplish any intellectual task that human beings can perform. Criterion 2. An AI is called AGI if it surpasses human capabilities in the majority of economically valuable tasks. The first criterion doesn't quite apply in our case because the decision-making process in financial services already heavily depends on computing machines. The second criterion is perhaps a better fit. Perhaps the single biggest shortcoming of financial institutions is that they are divided into many loosely coupled decision silos. These include asset class silos, trading book and banking book, rates, FX, equities, commodities, credit. Function silos, trading, risk management, treasury, back office, sales. Silo-specific, inconsistent models. Data silos and communication silos. Client-specific silos, for value adjustments or collateral add-ons. Breaking down these silos is recognized as perhaps the biggest challenge facing the banking industry. Even the most recent bank defaults have been attributed to the separation between funding risk management on the asset side and the liabilities side. If an artificial intelligence were able to break down these boundaries, we would undoubtedly generate a great deal of economic value, and I would be happy to call it AGI. In conclusion, we have discussed some applications of clearinghouse analytics, emphasizing their relationship with AI technologies. Both enterprise-level analytics and permissioning are highly useful for managing WWR, reverse stress testing, cross-margining, and regulatory supervision strategies. LLM integration requires a modeling language for risk and pricing, as well as a separate solver that factorizes all complexities in a completely generic way. Global Valuation has developed a compiler solver technology based on matrix engines, which can scale to enterprise-level problems, as demonstrated in our case study. Here is a list of papers we wrote which are relevant to the topics we covered today. For a more complete selection and additional information, please visit our company website at www.global-valuation.com.